All right, so in this video, we're going to cover the rest of Lab 4. The first part was covered in a previous video recorded last semester, so notice some of the numbers don't line up maybe the same, but you can still answer all these questions, or if you got stuck, we'll work on that on Friday. So we're going to continue with expected value. Expected value is the way to think about the value of a decision with multiple outcomes. So let's look at, I'll explain two ways without thinking about it, but using the example of a raffle ticket. A raffle ticket is something you buy with the potential of winning some kind of reward. So here's a charity that's selling 2,000 tickets. The tickets cost $5, and only one of them will win. We randomly pick one of them to win. And the prize for winning is $4,000. Seems like a pretty good deal. Let's see. So the first way to think about it is, this is just my notes. You can write it down if you want, but average gain or loss. That's the first way. So the way we can calculate this is the gain, the loss, and the average. Gain is like the profit, loss is like the expense, and then I should say income. Gain is the income. I'm really not in the business. I should have these terms better. Income, expense, and then profit. This is like the total, the net. Okay, so let's find that. What's the total income you make if you're the charity on this? So that's 2,000 tickets. We're selling tickets times $5 per ticket. So that's going to be, what, $10,000? Yeah, that's how much profit income you make. The expense is the negative, the $4,000. You still have to give $4,000 to the person that wins. So the net profit is 10,000 minus 4,000. So that's 6,000. That's how much we made total. Okay, so what's the average gain per person? If there was $6,000 and there were 2,000 tickets, you can calculate that as $3 per ticket. That's the average gain or loss per person for this situation. And that's the first way of thinking about the expected value, the average gain or loss over many, many trials. The other way you can think about expected value is using probabilities. So if we have two events, A or B, we could say the value of A times the probability of A plus the value of B times the probability of B. So that's what we'll do next. Okay, so let's do the same problem using that framework. So what's the value of winning? And this will be now from the perspective of the person buying the ticket. If they win, they get $4,000, right? But remember, you still spent $5. So we have to minus 5 from that. What's the value of losing? Is just minus 5. You spent $5 and you don't get it back. And then what's the probability of winning? Remember, 1 out of 2,000 tickets wins. So it's 1 out of 2,000. And then looks like I have value of losing twice. You can get rid of one of those. Probability of losing. Notice you either win or you lose. So those are complementary events. Probability of losing would be 1 minus probability of winning. So I set these up to calculate each of those. And if I have these correct, then this next line has my expected value formula. This value times this value plus this value times this value. So let's run it. You'll see -3. This means on average, if you're playing this raffle, you're losing $3 or you're giving $3 to the charity, whichever way you like to think about it. So that's a good example. All right, I want to let you work on the next problem by yourself. You can talk about it in class if you want, But my first tip will be copy paste what you're saying here, and then decide what winning and losing mean. I might say like winning is no earthquake, and no earthquake, what are the probabilities and values of no earthquake, and then losing is when there is an earthquake. Those are the two outcomes in the situation. So see if you can modify these numbers to fit that. And then the same formula will apply if you put the numbers, the probabilities and values in correctly. All right, so once you finish that, you can pause this video. I'm going to cover the last section, which is conditional probability. So I want to use this table that's in section 382 of your textbook to talk about conditional probability. Now it's also in the lab. So if you go under lab 4, you'll see this table here. What's going on with this table? It's talking about 2 different outcomes for something that Google's now doing all the time with the photos that are uploaded. They're trying to determine like what's going on. Is this a photo of polar gear or not, you know? And so it uses algorithms called machine learning to predict whether this is a photo of someone or if it's a photo that's about cats or it's about fashion. In this case, we're looking at fashion, something that has some kind of commercial interest. So as humans determine, there's either the truth that the photo is about fashion or it's not about fashion. So what this table says is 309 photos were about fashion, 1513 were not, and there was a total of 1822. You add these 2 numbers together and you get the total. Okay, that's what's going on with the columns. Excuse me. Now the rows are what the machine learning, what Google's predicting. I'm going to see how accurate it is. So if it's predicting that the photo is about fashion, there was 219 that it predicted about fashion. Of those, 197 were accurate. It predicted the photo about fashion was about fashion. 22 were not. And so then we also see the predictions that were not about fashion. There were 112 that were predicted fashion. So that's like not accurate. It was about fashion, but it predicted not. And there were 1491 that were not about fashion that it predicted not. And so let's just do a quick check of independence. Independence would mean these 2 events don't affect each other. Whether or not it's about fashion shouldn't affect the probability. So let's see. Let's find, and I'm going to use conditional probabilities for this. So this is just kind of some notes for your lab. Conditional probabilities are read probability of B given that A has occurred. Probability of something given that something else has occurred. So let's look at an example. Probability of predicting fashion given not about fashion. And probability of predicting fashion given about fashion. We're going to see if these events are independent. If they're independent, they should be the same, right? Okay, I can't type, but I'm going to use some little code chunks. You can add this if you want or write it down for your own notes. So fashion. So we're going to find these 2 probabilities. This is read, again, probability of predicting fashion given the photo is not about fashion. So let's go back to our table here. So if the photo is not about fashion, given the photo is not about fashion, that would be this category here. So predicting not about fashion, 1491 of those. 1491 predicted fashion. Oh no. 22 predicted fashion. Excuse me, 22 of the not about fashion predicted fashion. So 22. And not about fashion was total of 1513. So that's the probability of predicting fashion given that it's not about fashion. 22 of the total, not about fashion. So 1.4%. Now let's look at the probability of predicting fashion given that it's about fashion. So if it's about fashion, that's this column. What's the probability of predicting fashion is now 197. 197 over 309. Total of the fashion photos was 309. So, bam, look, these probabilities are very different. Probability of predicting fashion depends very much on whether the photo is about fashion or not. So this is a good example of when we can no longer use independence events. These events are affecting each other. Whether the photo is about fashion or not will affect whether it predicts about fashion or not. That's what we want for machine learning. We want it to be accurate. So for finding probabilities with conditional, these are called conditional events. They affect each other. So for finding these probabilities, we have a different formula. Notice probability of A and B before was probability of A times probability of B. Now it's not so simple. Now probability of A and B is probability of A given that B has already occurred times probability of B. There's some kind of information that has to be included. So I can also solve this for this. Probability of A given B, I can divide by probability of B on both sides. And so that gives me another formula that I can use for finding conditional probabilities. So let's do it. Let's do it in some examples. I'll do the first examples with you, the first two, and then we'll leave the rest of them for you. So here's the first one. Find the probability that prediction was correct given that the photo was about fashion. So we can write it like this. If it's correct, given the photo is about fashion, that's the truth is fashion. It's correct when it predicts fashion. So I'm going to say A is predicts fashion and truth is fashion. So let's use, for starters, this formula here. I'll say probability of A and B. That's just a way I can write it, P underscore A and B, and I'll find that probability. And then I'll say PB, I'll find that probability. And then I can say the conditional probability is PA and B divided by P probability of B. And that will find it for me. There we go. So let's first find probability of A and B. That's probability of predicting fashion and the truth being fashion. So predicting fashion and truth being fashion, which events had both those? That would be these. So 197. 197 had both, predicting fashion and the truth being fashion. And we could see that that's out of a total of 1822. Nice. Okay. Then we got to find what's the probability of B, truth being fashion. Truth being fashion is this column. So 309 is the total of photos that were about fashion. And that's out of a total of 1822 again. 1822. So you can run that. And that gives us about 63%. Okay. That's using the formula. The other way to think about it is saying, given that the truth is about fashion, we're looking at this column here. We can isolate, we can get rid of everything else and see we're only looking at these 309 photos. How many of them predicted fashion? So that'd be 197 predicted fashion out of 309. So that would be 63%, same thing. So two ways to think about it. And I recommend kind of practicing with both. And then that way you have one that might make more sense to you or that you just like more and you can keep doing that. Okay, so let's break down. Hopefully that was helpful, that explanation. If not, you can watch it again. You can pause and rewind because there is a lot of information in these two-way tables. So I'm going to go through the next one with you, break it down the same way. So first step is, what does the problem say? The probability that machine learning was correct. So I will say probability machine learning was correct, given that the photo was about fashion. So, oh, not about fashion. truth is not about fashion. So A would be, so if B is not about fashion, truth is not fashion, if the prediction is correct, it should predict not fashion, right? So we'll use these as our events. So not fashion, not fashion. Truth being not fashion and predict being not fashion would be these two, right? Not fashion and not fashion. So 1491, 1491. And then we want to find the probability. That was probability of A and B. Now probability of B is not fashion. Truth being not fashion. Notice there were 1513 total on not fashion. 1513. You could run that and see, ooh, 98%. It's correct 98% of the time. And so that's the first way to think about it. Let's do the second one. Given the truth is not fashion, we're looking at this column here, not fashion. Given the truth is not fashion, how many were correct, predicting not fashion? So it'd be 1491, 1491 divided by 1513, total not about fashion. Oops. There we go. Same answer. All right. So now you can get the other two. And you can use that to say, hey, when is machine learning the most accurate? All right. And there is a bonus section on Bayes' rule. This has some more detailed math on some of the math that's behind machine learning as well, if you're interested. All right. So that's all. We'll see you guys on Friday for this material.